In this tutorial, I will explain how to build a quarter wave ground plane antenna. The antennas built in this tutorial are intended for test and educational purpose and should be used indoors. The antennas are constructed in such a way so it can be easily disassembled and its parts can be reused in other antenna projects. The antennas are not properly constructed and the antenna performance can be improved by using better materials, parts, or another way of construction. The quarter wave ground plane antenna, aka spider antenna, has radials. Often 4 quarter wave radials are used to sufficiently simulate a complete circular conductive ground plane which works as a reflector, as already explained in tutorial 42. The current in the reflected image has the same direction as the current in the real antenna. If the radials are straight, meaning not bent, the impedance at the feed point will be around 37 ohms. If the radials are bent down at an angle of 40 degrees, the impedance at the feed point will be around 50 ohms. The quarter wave ground plane antenna is an unbalanced antenna, thus a 50 ohms coax cable, which is an unbalanced feed line, can be directly attached to it. Here you see a quarter wave ground plane antenna. This is a coax cable, the 4 radials, and here is the radiator. The quarter wave ground plane antenna has one radiating element, as you can see over here, which is fed at the lower end, here, which is near the conductive surface. The radiating element length, this length, is a quarter wavelength in length, and the radials are slightly longer. The radiating element is also called the driven element, radiator, or resonator. I have modeled the quarter wave ground plane antenna in the 4NEC2 program using these antenna parameters and symbols, also known as variables. The radials are bent at an angle of 40 degrees. The radiator length is a quarter wavelength. The feed point is located here. And the antenna is positioned at a height of 11 meters. The 4NEC2 card deck can be found at this location. These are the symbols I have used. When the radiating element length is 86.345 millimeters, the phasor is 1.51 and the corresponding maximum gain is 5.77 dBi. You can see the phasor over here. Here you see the corresponding radiation patterns. Here is the radiation pattern in the vertical plane and the radiation pattern in the horizontal plane. And here you can see the maximum gain is 5.77 dBi. Again, the radiation pattern in the vertical plane and the same radiation pattern in the 3D view. This is how the quarter wave ground plane antenna looks like in a 3D view, as you can see over here. And again, the radiation pattern in 3D. Please be aware that the generated radiation patterns are merely a rough indication how the real quarter wave ground plane antenna behaves. The real quarter wave ground plane antenna is not 100% accurately modeled. If you want accurate radiation patterns of real antennas, then the antenna radiation patterns measurements should be performed in an anechoic chamber. As mentioned earlier, if the radiating element is 86 mm long, then the phasor is 1.51 and the corresponding maximum gain is 5.77 dBi. If the antenna model is optimized by changing the radiating element length to 82 mm, you get this length by multiplying this length by the velocity vector of copper. In this case, the phasor is 1.18 and the corresponding maximum gain is 5.82 dBi. Using the optimized quarter wave ground plane antenna with this length and this ground type and this card deck, I get these results. If the antenna is 1 meter above ground, the phasor is 1.19 and the corresponding maximum gain is 5.99 dBi. If the antenna is positioned 11 meters above ground, you get these results, etc. In free space, the phasor is 1.18 and the maximum gain is 1.48 dBi. As you can see, the higher the antenna, the lower the maximum gain, from 5.99 dBi to 1.48 dBi. I have done the same using the optimized half-wave dipole antenna with a length of 160 mm. See tutorial 41. The 4NC card deck can be found at this location. And you will see the same behavior. The higher the antenna, the lower the maximum gain. Based on the 4NC2 antenna model results, the half-wave dipole antenna has a slightly higher maximum gain compared to the quarter-wave ground plane antenna. Based on the previous slides, you might think by placing the antenna near the ground, you will get the best antenna performance, meaning higher gain. But placing the antenna near the ground is not a good idea because of the Fresnel zone. If you do not know what the Fresnel zone is, watch tutorial 7. This is the Fresnel zone. The quarter-wave ground plane antenna pros and cons. The pros: provides good performance, easy to build with consistent results, can be used at all frequency bands including low frequency, medium frequency, high frequency, very high frequency, and beyond. Omnidirectional radiation, vertically polarized signals, low cost, low angle of radiation, which means the signal is not directed towards the sky. And the radiation pattern is fairly uniform, both vertically and horizontally. The cons: the antenna requires a ground plane, meaning using radials, and a half-wave dipole antenna has a slightly higher maximum gain compared to a quarter-wave ground plane antenna. Now let's see what is needed to build a quarter-wave ground plane antenna. You need a Type N female chassis mount 4-hole connector. It has an impedance of 50 ohms. Optionally, you can use a Type N male to RP-SMA male plug adapter coaxial cable connector, an RF coaxial cable RG316. The length is 20 centimeters with a Type N male plug right angle to SMA male connector. You can use an outdoor electric cable. This copper wire has a diameter of 1.8 millimeters. Only 1 meter is needed. The electrical insulator can be easily removed using a Stanley knife. The copper wire can be stretched out. The stretched out wire will be stiffer, more straight, and the wire diameter will decrease. In my case, the wire diameter decreases to 1.65 millimeters. Next, a terminal strip block is needed. This terminal strip block is used for electrical wires with an area of 1.5 to 4 square millimeters. A total of 5 terminals with corresponding screws are needed. You also need 4 metal washers. The terminal screw head diameter, which is 3.5 millimeter, is the same size as the Type N connector hole diameter, which is also 3.5 millimeters. And that is why metal washers are needed, as you can see over here and here. This is the Type N female chassis mount 4-hole connector, the radiator, 4 radials, 4 metal washers, 5 terminals from this terminal strip block. From one terminal, I cut the screws in half, as you can see here. To cut the screws in half, I use a wire cutter. Completely screw it in and then cut it. If I take one terminal, it does not fit. Use a punch to enlarge the hole. The hole in this terminal is enlarged. It will now fit. The head of this screw easily goes through this hole. To prevent this, use a metal washer. Now the screw does not fall through. These terminals comes from this terminal strip block. But there are many other terminal strip blocks, like this one. Here you see the two terminals. I prefer using this terminal because it is much smaller. Now let's assemble the quarter wave ground plane antenna. Attach the four terminals. And these are the four metal washers. Attach the radials. The four radials are attached. Now attach the radiator. The radiator is attached. Make sure this screw does not touch the ground. And check the radiator length. As you can see, my radiator length is 86 millimeters. You can use the RF coaxial RG316 with type N male connector to SMA male connector. Or you can use a type N male to RP SMA male plug adapter coaxial cable connector. Alternative components or methods can be used to build the quarter wave ground plane antenna. Here are just a few suggestions. Use aluminium or copper tube instead of wires because copper wires bend easily. If the type N female chassis has a silver coating, the radials can be soldered onto the chassis. In this case, no terminals are needed. Instead of terminals, attach crimp terminal rings to the radials. Make a wire loop at the end of each radial. In this case, no terminals are needed. Instead of the type N female chassis, as you can see over here, use a SMA female chassis panel mount 4-hole flange. Instead of the type N female chassis, use the SMA female PCB mount straight RF connector. You can solder the radiating element over here and the radials at these ends. If you have a type N female RF connector with no flange, as you can see over here, you can use a metal ring washer. Drill 4 holes, and this ring can be used as a flange. Here is the quarter wave ground plane antenna fully assembled. This is the radiating element, and these are the 4 radials. As you can see over here, these are the 5 terminals. This is the bottom view, and as you can see over here, these are the washers. Please note, using terminals with screws does not improve the antenna performance. Watch out, this screw must not touch this ground. As you can see over here, the radial is bent, and the radial is attached to this terminal using this screw. Here is another view. A coax cable is attached to the quarter wave ground plane antenna. The quarter wave ground plane antenna attached to the end node using a coax cable. And here the quarter wave ground plane antenna without using a coax cable. The quarter wave ground plane antenna attached to my end node without using a coax cable. If the frequency is 868 MHz and the light speed is this value, then the wavelength can be calculated using this equation. So for a frequency of 868 MHz, the wavelength is 345.38 millimeters. If the radiating element is made of copper, the velocity factor is 0.95. The radiating element length is calculated with this equation, and the result is 82.03 millimeters. Usually, the radial length is 5% to 12% longer than the radiating length. The radial length is measured from the base of the antenna. Make the radial length 10% longer than the radiating length. The radial length is 82.03 times 1.1 equals 90.23 millimeters. Here's an overview. The radiating length is calculated with this equation. L radial is this length plus this length, and L radial is 1.1, that is the 10% part, times L radiating. This length is measured from the base of the antenna to the top of the antenna, and this length, LA, starts from the center of the antenna till the end of the terminal. Again, this length is measured from the center of the antenna till the end of the terminal, and this length, LB, starts from the end of the terminal till the end of the radial. Because I have this antenna analyzer, I made my radiating element length 86 millimeters instead of 82 millimeters, so I can use my antenna analyzer to tune the antenna. I have made my radial element length 90 millimeters. The radial elements are bent down at an angle of 40 degrees. This will change the impedance at the feed point to be around 50 ohms. So if you do this calculation, you will get a radiating element length of 82 millimeters. But instead, I have made my radiating element length 86 millimeters, so I can tune it with my antenna analyzer. This length is 21 millimeters. I made a total radial length 90 millimeters, that is this length in total. If you use this equation, the length LB will be 69 millimeters. So I made this length 69 millimeters. This length is 69 millimeters, and I've made this length 8 millimeters. Why? Because this part goes inside this terminal. In the previous slides, I have shown how to build a quarter wave ground plane antenna. The demonstrated antenna is not intended to be used outdoors. The components I have used will not withstand harsh weather conditions. The tiny screws will loosen and the copper wires will bend from wind and other weather conditions. The quarter wave ground plane antenna can be used outdoors, but use stronger and tougher components that can withstand harsh weather conditions. For example, use large crimped terminal rings, bolts, nuts, and washers to firmly attach the radials to the Type N connector. Use copper or aluminum tubing instead of wires. The quarter wave ground plane antenna directly attached to the antenna analyzer. In my situation, I got the best antenna performance when the radiating element length is 86 millimeters. The phase wire is approximately 1.1, the impedance is approximately 51 ohms, and S11 is approximately minus 25 dB. Here you see the corresponding phase wire plot and S11 plot, and the corresponding impedance plot. The quarter wave ground plane antenna performance is compared with a sleeve dipole antenna. More information about sleeve dipole antennas, see tutorial 43. For this test, I'm using the end node and antenna C as demonstrated in tutorial 33. More information about this end node, see this web page. The end node uses the MCCI LoRaWAN LMIC library. See this GitHub page. The end node uses the following sketch. See this link. Here you see the quarter wave ground plane antenna directly attached to the end node. And here the sleeve dipole antenna is attached to the end node. The end node is placed inside the building in front of a window. This is the building circumference. The end node is placed at location A, facing east and south, at an altitude of 11 meters. I have not modified the end node transmission power when using the quarter wave ground plane antenna. In my area there are several gateways, and I know that these gateways, which are connected to the Things network, can receive my transmitted data. The quarter wave ground plane antenna is attached to the end node at location A and transmits data. I have done the same with the sleeve dipole antenna. In both cases, 2 messages per minute were transmitted. The logged data can be found at this location. One or more gateways were able to receive my transmitted sensor data. See this Google map. The end node transmission power is 14 dBm. This table is created with the help of the logged data. These are the gateways which were able to receive my transmitted sensor data. These are the distances between the end node and the gateway. These are the gateway antenna altitudes. These are the average RSSI values for the quarter wave ground plane antenna, and these are the average RSSI values for the sleeve dipole antenna. These asterisks means there were only one or few measurements, and I will ignore these results. If you look at the results, you may notice there is no significant difference in the average RSSI values. When using the quarter wave ground plane antenna, it took 17.5 minutes to transmit 30 messages. When using the sleeve dipole antenna, which is my reference antenna, it took 18.5 minutes to transmit 15 messages. The Arduino sketch is configured to transmit 2 messages per minute. In a perfect situation, it should take 14.5 to 15 minutes to transmit these 30 messages. So looking at the results, I can conclude that my self-built quarter wave ground plane antenna performs the same as a sleeve dipole antenna. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.